Hi everyone and welcome. In this lecture I want to go over eigenvalues and eigenvectors, basically show you what they are and how we can find them. So one thing to not forget, we always going to be dealing with square matrices and by n matrices. So what's the question? Question is, do non-zero vectors x in Rn exist such that the matrix A times x is a scalar multiple of x? So the scalar multiple, in this case, we call it lambda, the Greek letter, which is the eigenvalue. And of course, x is the non-zero vector. We call it the eigenvector. We want to know if we can have that relation. A times x equals to lambda times x. And again, x's are the eigenvectors. Well, the x here is written twice, and lambda is our eigenvalue. So to show it in R2, when you take a vector and you multiply it by a scalar, you get the same vector in the same direction. The question is, we can get that by matrix multiplication, by that relation. And that's for lambda positive, and if lambda is negative, it's going to go in opposite direction. So definition, let A be an n by n matrix. The scalar lambda is called the eigenvalue of A when there is a non-zero vector x such that we can have that relation as we just talked about it. The vector x is called the eigenvector of A to the corresponding eigenvalue. Now if we have a vector in R2, so that's the eigenvector, and the eigenvalue is 2. Let's verify if that's true. So the way you can verify that is just on one side do A times x. So A times the vector. So if you do that, 2 times 1 is 2, 0 times 0 is 0, so you get 2, 0 times 1 is 0, and negative 1 times 0 is 0, you get 0. And if you multiply 2 by the same vector, then you get both sides, the left side and the right side, to be equal. So that's how you can verify it. You can do the same thing with this vector and that eigenvalue on your own, and you see you'll get the same answer. I did another one uh, with a 3 by 3 matrix. So we have these eigenvectors. We want to find the eigenvalues. So you can take the matrix, multiply it by the eigenvector. So if we do this, 3 times negative 3 is negative 3, negative 2 times negative 1 is 2, and 1 times 1 is 1. Basically, you get negative 3 plus 3 is 0. Second row is all zeros times those is going to give you 0, and 0 times negative 3 is 0. That's going to give you negative 1, and that times that is 1, so you get 0. So the question is, what number you want to multiply this vector to get zeros, and of course that number is 0, so the eigenvalue is 0 here. For the second one, if you try the multiplication, you get this side. If you do that multiplication, try it please, you get the same vector. So the question is, this vector times what number is going to give you the same vector, and it's 1. It's pretty easy to verify. We're dealing with vectors, so let's talk about eigenspaces. Each eigenvalue can have infinitely many eigenvectors. For the first one, for example, verify the first matrix. This, both of them can be the eigenvectors for the eigenvalue 2. So now what's the conclusion? If A is an n by n matrix, an eigenvalue with an eigenvalue lambda and the corresponding eigenvector x1, then every non-zero scalar multiple of x is also an eigenvector. So if you find the eigenvector and you multiply that eigenvector by any non-zero scalar, that new vector will also be an eigenvector. The proof of that, you can say A times C of x. You can write that as C times A times x. So, but what is A times x? A times x is just lambda x. So we have that relation, and you know by uh, associative property, you can write this as lambda times C of x. So what we did, we started by A times C of x, and we have lambda times C of x. So we have the relation. So therefore, C times x is also an eigenvector. This is also valid if x1 and x2 are eigenvectors, then the sum is going to be also an eigenvector. So you can start with A times x1 plus x2. You can distribute the A, so you get A times x1 plus A times x2. But what is A times x1? That's just lambda times x1 plus lambda times x2. And you can factor out lambda, so you get lambda times x1 plus x2. Again, we started with A times x1 plus x2, and we ended with lambda times x1 plus x2. So this is an eigenvector. Next, the set of all eigenvectors of a given eigenvalue lambda together with the zero vector is a subspace of Rn, and that's called the eigenspace. So if an n by n, this is basically the theorem, is the same thing. If an n by n matrix with eigenvalue lambda, then the set of all eigenvectors of lambda together with the zero vector, you know, it's a subspace, so it has to have the zero vector, is called the eigenspace, and basically that's another way of writing that. So now how do we find eigenvalues and eigenvectors? We have an n by n matrix will be given, and you know the identity matrix. So you can write that relation, but you can multiply the right side by I, and when you do that, basically you get a square diagonal matrix with the same number. You can take everything to one side, factor out x here, so you get this homogeneous system. So that's a homogeneous system. Now we know that the homogeneous system of equation has non-zero solutions if and only if lambda minus r, or that matrix, is not invertible or the determinant equals to 0. So what you want to know is take the determinant of that matrix and put it equal to 0. So, and that's what it says here. Eigenvalue of A is a scalar such that the determinant of A minus lambda I, or it's the same thing. You can see that one. They're both basically the same, and they're going to give you the same answers. And you put it equal to 0. Once you find the eigenvalues, then the eigenvectors, you take the same matrix times x and put equal to 0. This is a homogeneous system. You solve for x's, and that's going to give you the eigenvectors. So now this equation that we saw is called the characteristic equation of A. When you write that, we're going to do an example. You do get a polynomial like that. So you put equal to 0, you solve it, and you can find the eigenvalues. Let's do a little example here with the 2 by 2 matrix. So again, this matrix here is 2 minus lambda, and all you do is just take the diagonals and minus lambda, or lambda minus diagonals. It doesn't make any difference. You find the determinant of that. This is a 2 by 2 matrix. The determinant is that times that minus that times that, which is right here. Simplify the equation, you get lambda squared plus 3 lambda equals to 0. You can factor out that you get lambda plus 1 times lambda plus 2 equals to 0. You have two eigenvalues here. So once you have your eigenvalues, then we're gonna find the eigenvectors by solving this homogeneous equation for both lambdas separately. If lambda 1 equals to -1, then the system that you can write again, the coefficient or matrix is going to be 2 minus negative lambda and -5 minus lambda, which is -1 here. So you get that matrix. You can write the system and solve it. And basically what you do is find the row reduced form of the matrix of the coefficient, and that's what you get. As you see, we have one non-pivot column here, and that's the free variable. So you can we have we have done a lot of those systems before to find that, just like finding the null space of the matrix of a matrix. It works the same way. The free variable here is x2, so you can write x1 with respect to x2 or in function of x2. That's what you get. You write your vector instead of x2 here, you could have just put t. It's the same thing. And then if you find, what you get is x1 1 over 4. So you can do x1 1 over 4, or if you take 1 over 4 x1 out, you just get 4 1. It's the same thing. So this is the eigenvector corresponding to the eigenvalue lambda equals to -1 here. So let's go over the steps. If you want to find the eigenvalue and eigenvectors, form the characteristic equation a minus lambda equals to 0, or lambda minus a equals to 0 is the same thing. That's a polynomial of degree n. Find the solutions or the roots of those polynomials. These are your eigenvalues, or the eigenvalues of a. For each eigenvalue lambda I, find the corresponding eigenvector by solving the homogeneous system. That system, we just did that in the example. Please double check that example again. And that requires some row reducing. Basically, it's just finding the null space of that matrix. Now there's a note here, we're going to see this in the next lectures. The multiplicity of eigenvalues greater or equal to dimension of the eigenspace. We'll see that later on. And I put a theorem here for you. The eigenvalues of a triangular matrix, if we're dealing with a triangular matrix, then its eigenvalues are the entries of its main diagonal. That goes with the diagonal matrix also. So I think that's good enough for this lecture. Please watch this couple of times, and in the next lecture, I am going to talk about diagonalization and how you can use the eigenvalues and the eigenvectors to diagonalize a matrix, and why a diagonal matrix is always very helpful. We're going to go over that. I'm going to stop here for this one. And again, please watch this couple of times, and I will see you in my next lecture. Have a great one, everyone.